Here's something that might completely flip your understanding of our sun. The scorching temperatures we've been measuring in solar flares? We've been looking at this phenomenon all wrong for nearly 5 decades. When our sun unleashes its most violent tantrums, those spectacular eruptions of magnetic energy we call solar flares, the resulting chaos can wreak havoc on everything from your GPS navigation to communication satellites orbiting Earth. These cosmic explosions represent our star operating at maximum intensity, pumping out enough energy to disrupt radio transmissions and pose genuine threats to both spacecraft and the brave astronauts aboard them. But here's where it gets controversial. Scientists have been making a fundamental assumption about these stellar outbursts that might be completely backward. For generations, the scientific community operated under the belief that during solar flares, the plasma soup of charged particles quickly reaches thermal equilibrium, meaning electrons and ions settle into roughly the same temperature range. This assumption made calculations neat and tidy. But what if reality during these explosive events tells a dramatically different story? A groundbreaking investigation spearheaded by Alexander Russell from the University of St. Andrews has just shattered this long-held scientific assumption with findings that are nothing short of revolutionary. The research team discovered something that challenges decades of established thinking. During the most critical phases of solar flares, ions become exponentially hotter than electrons. And we're not talking about minor temperature differences here. The numbers are staggering. These ions reach temperatures approximately 6.5 times higher than their electron counterparts, with ion temperatures likely soaring beyond 60 million degrees Kelvin. To put this in perspective, that's roughly 4,000 times hotter than the sun's surface temperature. This revelation provides an elegantly simple explanation for one of astrophysics' most persistent puzzles: why certain spectral signatures in solar flares appear abnormally broad. In our measurements, for almost half a century, researchers have been scratching their heads over these mysteriously wide emission lines, typically attributing them to turbulent plasma movements that nobody could quite pin down. And this is the part most people miss. The answer might have been hiding in plain sight all along. Understanding the plasma battlefield. To grasp why this discovery matters so profoundly, imagine solar plasma as an incredibly hot soup containing 2 main ingredients: featherweight, negatively charged electrons zipping around alongside much heavier, positively charged ions, essentially atoms like iron and calcium that have been stripped of their electrons by the extreme conditions. Traditional solar physics models operated on the assumption that these particles would quickly bump into each other during flare events, sharing their energy like billiard balls until they reached a common temperature. This assumption streamlined mathematical models, but it may have been masking the true nature of what happens during the sun's most violent episodes. Russell's research team took a step back and examined the fundamental heating mechanics occurring during flares, drawing inspiration from a growing collection of evidence gathered from space plasma environments much closer to home. The universal reconnection rule. Here's where the story takes a fascinating turn. Throughout our solar system, from the solar wind streaming past Earth to the plasma environments near our planet, scientists have repeatedly observed a phenomenon called magnetic reconnection. This process occurs when stressed magnetic field lines suddenly snap apart and rapidly reconnect, releasing enormous amounts of stored energy. What's remarkable is that this reconnection process consistently heats ions approximately 6.5 times more than electrons, following what appears to be a universal physical law. Russell explained their excitement. Recent discoveries revealed that magnetic reconnection heats ions 6.5 times as much as electrons. This appears to be a universal law, confirmed in near-Earth space, the solar wind, and computer simulations. However, nobody had previously connected this research to solar flares. When you apply this universal rule to solar flare dynamics, you arrive at a dramatic and testable prediction that changes everything. During the early stages of a flare, particularly in the regions high above the brilliant loops of superheated plasma, ion temperatures can rocket past 60 million Kelvin, while remaining significantly hotter than electron temperatures for extended periods, sometimes lasting tens of minutes. But here's where it gets controversial. This temperature differential fundamentally alters how we should interpret telescope observations that have guided solar physics research for decades. Decoding the spectral mystery. Spectral lines, those bright signatures appearing at specific ultraviolet and X-ray wavelengths that telescopes detect, become broader when the particles emitting them move faster due to higher temperatures. For nearly 50 years, these unusually wide spectral lines were consistently blamed on unresolved turbulent motions within the flare plasma. The new research suggests that superheated ions could be responsible for a significant portion of that extra spectral width, not the turbulence that scientists have been chasing for decades. Think of it this way. When ions are blazing hot, they vibrate more vigorously, causing the light they emit to spread across a wider range of wavelengths. This broadening effect can look identical to turbulence signatures, which explains why researchers spent decades debating what physical processes were supposedly stirring flare plasma so intensely. Russell's team demonstrates why ion-dominated heating during flare onset, particularly in the above-the-loop regions where reconnection outflows collide with denser plasma, naturally produces the observed line widths that have puzzled scientists since the 1970s. The new ion temperature fits remarkably well with flare spectral line widths, potentially solving an astrophysics mystery that has persisted for nearly half a century, Russell noted. Timing makes all the difference. A crucial factor enabling this explanation involves timing and plasma density. In the dense, cooling loops that form after a flare reaches peak brightness, ions and electrons collide frequently enough to share energy and equalize temperatures relatively quickly. This is where the traditional equilibrium assumption actually holds true. However, higher up in the solar atmosphere, where plasma densities are significantly lower, particle collisions become much rarer events. This means the dramatic ion-electron temperature gap can persist long enough to leave clear fingerprints in the flare's spectral signature. The research argues that previous equilibration estimates were often based on conditions within dense loop structures, not the more rarefied, earlier stage or higher altitude regions where magnetic reconnection performs its most intense work. Revolutionary implications for solar physics. The elegance of this proposal lies in its simplicity. It doesn't require inventing radical new physics. Instead, it borrows a well-supported heating ratio from reconnection studies conducted throughout the solar wind and Earth's magnetosphere, then applies this established principle to regions where reconnection activity peaks on the Sun. The result creates a unified theoretical framework. Magnetic reconnection preferentially energizes ions. Low plasma densities at high altitudes allow this temperature advantage to survive, and these hot ions inflate spectral lines that have appeared non-thermal for generations. If this interpretation proves correct, it fundamentally reshapes how researchers should interpret decades of past observations and design future investigation strategies. Advanced instruments capable of separating emission lines from different ion types and comparing them with electron-sensitive diagnostics could directly test whether line widths correlate with higher ion temperatures rather than turbulent motion. This conceptual breakthrough also encourages computational modelers to allow ions and electrons to evolve independently during the crucial early minutes of flare development, rather than forcing them to share identical temperatures from the beginning. Space weather forecasting gets an upgrade. This discovery extends far beyond academic curiosity. Space weather prediction systems depend heavily on understanding how rapidly and how intensely flare plasmas heat up, because the resulting radiation bursts and particle storms determine their potential to disrupt Earth's ionosphere and threaten orbiting spacecraft. If ions capture the majority of thermal energy during initial flare phases, this dramatically affects energy transport mechanisms, shockwave formation, and particle acceleration processes, essentially the foundational elements that spawn the most destructive space weather events. The study also identifies new observational sweet spots for future research. Scientists should focus on early flare phases when the eruption is just beginning. Examine regions above the bright loop structures where reconnection outflows crash and churn, and analyze line widths from multiple ion species while comparing them with electron temperature diagnostics. If spectral widths align with the predicted 6.5 to 1 ion to electron temperature ratio, that would provide compelling evidence supporting this new interpretation. Russell and his colleagues demonstrate that abandoning this assumption, particularly during flare onset and within the thin, high-altitude plasma above loop structures, resolves a persistent spectral puzzle through one straightforward, physically motivated adjustment. Ions simply become much hotter than previously thought possible. This elegant solution connects our sun's most violent episodes to a universal reconnection principle measured throughout near-Earth space environments, while providing observers and theoretical modelers with a clear roadmap for investigating one of heliophysics' most enduring mysteries. But here's what makes this controversial. If this interpretation is correct, it means that decades of solar flare research may have been built on fundamentally flawed assumptions about temperature equilibration. What do you think? Could the scientific community have been missing this obvious explanation for nearly 50 years simply because the math was tidier with equilibrium assumptions? Or is there something about this new interpretation that doesn't quite add up? The research appears in the astrophysical journal Letters, and it's already sparking heated debates within the solar physics community. Some researchers are embracing these findings as the missing piece they've been searching for, while others remain skeptical about overturning decades of established theory. What's your take? Are we witnessing a genuine scientific breakthrough, or just another interpretation that will eventually be superseded by even newer discoveries? The comment section below is where the real discussion begins.